Hi friends, welcome. Friends, this is the question from 2009 question paper and it was for 2 marks. Here question is radiative heat transfer is intercepted between the inner surfaces of two very large isothermal parallel metal plates while the upper plate designated as plate 1 is a black surface and is the warmer one being maintained at 727 degrees Celsius. The lower plate, that is plate 2, is a diffuse and a grey surface with an emissivity of zero point 0.7 and is kept at 2 to 7 degrees Celsius. Assume that the surfaces are sufficiently large to form a two surface enclosure and steady state conditions to exist. Stephen Boltzmann constant is given as 5.67 into 10 raised minus 8 watt per meter square Kelvin raised to 4. The irradiation in kilowatt per meter square for the plate 1 is here. Friends, these are the options. Now let's start with the solution. To understand this, we will first draw the diagram. Suppose here this is a first plate, that is black surface, and here it is a second surface, that is our gray surface. Okay, here this is black surface, here this one is a gray surface. Okay, and this black surface is maintained at temperature T1 and this gray surface is maintained at temperature T2. Is T1 is here we have 7 to 7 degrees Celsius and T2, that is gray surface temperature, is we have here 2 to 7 degrees Celsius and its emissivity we have here 0.7. Okay, this is plate 1 and this is plate 2. Okay, here friends, energy emitted by this black surface is given by, we will give it a name, that EB1. This is the energy emitted by black surface, and here this is the energy emitted by gray surface E2, and here one another energy also emitted from this surface, that is gray surface, which is 1 minus alpha into bracket EB1. This is because friends, here black surface emits energy EB1 and this energy incidents upon gray surface, and from this EB1 some of the energy is absorbed by the gray surface, which is given by this formula, that is 1 minus alpha, that is alpha is absorptivity. So total energy of EV1 is 1, here we have considered, minus alpha, that is absorptivity, into this energy EB1, which will give us the energy emitted by gray surface, which is equal to here fraction of energy reflected from surface 2. Okay, which is due to the surface 1, that is plate 1, that is EB1. Okay, now here friends, as we know these both are flat surfaces, so we know here we have F11 plus F12 is equal to 1, but as these both surfaces are flat, the shape factor of a flat surface with respect to itself is 0. That is, here shape factor of surface 1, that is plate 1 with respect to plate 1, is 0. That is, here we have F12 is equal to 1. Similarly, for surface, that is plate 2, here we have F22 plus F21 is equal to 1, which will give us F21 is equal to 1. That is, here friends, we have F12 is equal to F21 from these two terms. So here friends, energy incident upon plate 1, that is irradiation, is equal to radiosity of plate 2. So here we have now energy incident upon plate 1, that is irradiation is equal to radiosity of plate 2. Okay, now here friends, we will consider energy leaving from surface 2. Energy leaving from surface 2. As you can see here, this is because energy incident upon plate 1, that is irradiation, is equal to radiosity of plate 2, that is here energy leaving from surface 2. Okay, so here we have now E2, that is as you can see here E2 plus 1 minus alpha into bracket EB1. Okay, so here E2 plus we have now 1 minus alpha EB1. Okay, now we will calculate one by one here. Here E2. Now the formula which we are going to write is for non-black surfaces. Okay, so here E2 is energy emitting due to own temperature, as we have understood earlier. So here for E2, that is for non-black surfaces, we have here equation here epsilon sigma T2 raise 4, here T2 because surface 2 plate 2. Okay, epsilon sigma T2 raise 4. So now we will put the values. We have given values. E2 is equal to, we have now see epsilon is you can see here 0.7. Then we have here sigma given as here 5.67 into 10 raised minus 8, 5.67 into 10 raised to minus 8. Okay, and next we have here temperature is here. Now here friends, remember one thing, here Stephen Boltzmann constant value is includes Kelvin value. So here we need to convert this 227 degrees Celsius into Kelvin. So here 227 degrees Celsius plus 273 degrees Celsius will give us here 500 Kelvin. So here T2 we have now 500 raised to 4. Okay, now after calculating these all values, we will get E2 is equal to 2480.62 watt per meter square. Now we will calculate here next term, that is from the equation. This is first term, now this is second term. For this 1 minus alpha EB1. Okay, here this term is here fraction of energy reflected from surface 2, that is plate 2 here. Now we will simplify this equation further. So here we have 1 minus alpha into bracket, and now here we will further simplify it like here sigma T1 raise 4. Okay, this is like friends epsilon sigma T raise 4. How it is we will see now. So here this is again converted into 1 minus here epsilon sigma T1 raise 4. This is because friends, according to Kirchhoff's law, Kirchhoff's law. Okay, now Kirchhoff's law states that alpha, that is absorptivity, is equal to emissivity epsilon. Alpha is equal to epsilon. So we have put the value here, alpha is equal to epsilon. So now let's put the value in this equation. So here we have now this equation values, we will put 1 minus epsilon, we have here 0.7 into sigma, we have here 5.67 into 10 raised minus 8, and again we here convert T1 into Kelvin. So here as you can see, T1 is 727 plus 273 degrees Celsius, which is equal to here 1000 Kelvin. So now we will put the value here 1000 raised to 4. So after calculating this value, we will get here 17010 watt per meter square. Okay, now here friends, see, we will come here now for further calculation. So we have here these two values, as you can see, E2 we got here and this term we got here. This term has this value and this term has this value. Now we will go for this equation, and in this equation we will put this value and this value. As you can see, we have calculated and we will get the answer. So here now we have here total energy incident upon plate 1, that is here irradiation for plate 1 is equal to, we have here E2 plus 1 minus alpha EB1, which has values, as you can see here, E2 is this and this term is this value. So let's put the values. So 2480.62 watt per meter square plus 17010 watt per meter square. So after calculating, we will get here answer 19.49 kilowatt per meter square. So this is our answer for this question, and in the options here, as you can see, this is the near answer to this question. So option D is the correct answer. So here the irradiation for the plate 1 is 19.5 kilowatt per meter square. So friends, in this video we have understood how to solve problem based on isothermal parallel metal plates. Thank you friends for watching this video. Like, share and comment for this video and subscribe my channel. Thank you.